Hi Joshua. Let's
Hello.
continue applying the Euler's quotient or phi function in problem solving. So we have three problems to solve today. So number 5 is how many of the fractions below cannot be reduced to lowest terms or simplest form. So uh,
Okay.
so the fractions are from 1 over 24 2 over 24, 3 over 24, up to 24 over 24, meaning there are 24 fractions. How many of these 24 fractions cannot be reduced to lowest terms or simplest form?
In other words, those functions are already in simplest form.
Yes, so how many of those fractions are already in simplest form?
So to
Meaning,
yeah, okay.
meaning what?
Okay. So to define any such fraction already in simplest terms, it
You
means
can just put that here on the right side so we can utilize that space.
when a fraction is already in lowest
N
terms.
stands for
N is a numerator and D is denominator.
denominator.
Okay. So for any fraction n over d, where of course n and d are integers, are already in simplest form, it means that the GCD of n and d is equal to 1. It means they share no common factors, which is
Yes.
the very definition of the simplest term, to be in simplest terms. So in this case, the denominator is 24, so we can already point out that the GCD of any numerator of these fractions in already simplest form is of course 1. Okay. So now, to solve almost any GCD problem, we have to write out first the prime factorization of 24. So I'll just put it here.
Yes. Yes.
Okay. So phi of 24, the totient function of
Oh,
24.
put it a little below. It looks like a fraction. Or
Phi
provide
underline.
the underline
Phi of 24
or the quotient of 24.
using
One of
one
the
of the formulas. I'll
formulas that
just
we have discussed in our
red.
the, on,
Phi and yes.
video on the lecture about the Euler's quotient function.
Until of course 1 minus 1 over P and the final prime, of course. So here we will apply that. We now already know the prime factorization is just 2 and 3. So it's 24 times 1 over 1 minus the first prime, 2, and then 1 minus
Times
1
yes.
over 3, which is the second prime, and also the last prime. So then
You can
this
factor out there
is
and
24,
yes.
1 half, 2 thirds. And then of course 24 over 3 is 8. So already we can point out there are 8.
What do you
Those
mean
in
by the
okay.
phi function of 24 is 8?
Yeah, so those are the 8 totatives of 24 and I
Can
will
you write
just
the
list
8
down.
totatives of 24 there?
Those are 1, 5,
Write
7,
8 totatives
11.
of 24 for those who are
Yeah, 8
learning. Don't
totatives.
assume of 24.
1, 5, 7, I use
Use a different
different
color
color.
so that
1,
it will be more,
5,
it will look more
7,
artistic and
11,
use
13,
commas, use commas.
15, 19, 23. So
Meaning
these
these
numbers
numbers are
are relatively prime to 24. So of course they don't share it. That means they don't share any common factor with 24. And then one is a special case because one is counted as being relatively prime to all natural numbers. Yes.
Yes.
So
So that's it.
that's it.
So can it be reduced to simplest form or lowest terms, meaning you cannot reduce them further because they are already in their lowest terms. In lowest terms, as Joshua pointed out, the GCD of the numerator n24 is equal to 1. These are the numbers, eight numerators, which are relatively prime to the denominator 24. Okay, let's go to the next number, son.
Okay, so 6.
Can you put down this one? So I'll read the problem and you solve it. Given that the other prime factors of a certain integer n are 2 and 3, find in terms of n the number of positive integers less than or equal to n that are relatively prime to n. In terms of n, no, this could this sounds intimidating, but Joshua will show you that this is quite a simple problem.
It's not very hard.
Yes, it actually is a simple problem to solve.
So here, it explains that there's this integer n and are 2 and 3. So it means
2 and 3 are it's the prime
yes.
factors of n.
So the prime factorization of n is 2 to some exponent. I'm not going to specify anymore because we don't know yet.
Yes.
And then 3.
Nice.
Okay, so the number of positive integers less than or equal to n, the relative to prime to n. That's essentially the totient function of n.
Yes.
So we just need to find the totient function of n.
Can you show us the formula that you will use?
So in the previous page, I'll just copy from this previous page.
Yes. So use
And
red. Can you use red?
and Vn pala. Okay, Vn equals n times 1 minus 1 over P1, 1 minus 1 over P2, so on and so forth. And then 1 minus 1 over Pn, of course, the final prime. It has to end someday.
Where?
So,
The P. What are the P's
yes,
there?
P, where all splinter, all P, all such PI. Okay.
Right. Well.
The prime factors of n.
You just remove that one first, or you invert this one, so it doesn't give you that problem anymore.
Okay. So of course we know the prime factors of n. So in this case there's 2, 3, and then there are no other prime factors. So we don't need to use this part. So essentially we just need to write down n.
No, write it here to make it clear. Don't use the all does the space
Yes.
to utilize.
N, then 1 minus 1
No.
over.
Use of write everything. Not just the equal sign. The left. Think of our viewers as they're trying to learn. Don't assume that they know already.
Yes, okay, so n, of course, n times 1 minus 1 over the first prime 2 times 1 over 1 minus 1 over the second prime 3.
The
Last
second prime
one.
factor.
Yes, the second prime factor 3. And then simplify cancel. N over 3. So it is many words, but then there's not really much to the problem
Yes,
if you
so
analyze it.
this the final answer is n over 3. That's correct.
So actually, we have an example already of that. The 24 itself has only 2 and 3, and then guess what the totient function of 24 is? That's 24 over 3 or 8.
Yes. So
So we have that's
there,
proof.
if you torsion function of 24 is what is n? 24 over 3.
Actually, is 8.
Yes.
8. See, so they're the
Nice.
same.
You connected number 6 to number 5.
Yes. So
So
now we are moving on to the next
final
problem.
problem.
So now this problem
How
is
many?
much more direct than 6. But
Yes.
then this is the most complicated of them.
No, you just want to explain better. This is
Yes.
simple, but the solution to get to the final answer is easy. But just want to explain to our viewers what everything means. Okay.
Yes.
So how many numbers in 1 to 100 are co-prime to 100?
Yes. Okay,
So
so 200. 200 is equal to 2 times 100. So therefore, obviously, because 100 is literally in a possible factorization of 200, 100 and 200 cannot possibly be co-prime.
okay, let's write down everything so those uh, viewers who want to learn.
So since 100 and 200 are not co-prime,
Meaning,
yes, so 100 is not co-prime to 200. Oops.
meaning
Yes, they don't share it.
they
Yes,
share
they
common
can share common factors.
factors. Yes.
So because 100 and 200 are not co-prime, it means all numbers 1 to 200. Actually, this doesn't actually prove that all numbers 1 to 200 co-prime to 200 are also co-prime to 100.
Yes, they are.
No, it doesn't. Actually, we need to use the prime factorization. 100 is equal to 2 squared times 5 squared. 200 is also equal to 2 cubes times 5 squared. That they have the same primes. They have the same prime factors. So then we can say that all numbers 1 to 200 to 200 co-prime to 200 are also co-prime are also. Hmm. To 100.
Oh, hey, look at this statement. All numbers co-prime to 100 or co-prime to 100? What do you mean?
Ah, typo. 200. Yes. Okay. So all numbers
Ay,
100 to
now it makes
200
sense.
co-prime to 2. I did not
Co-prime to
notice.
100, also co-prime to 100, of course.
I did not notice
So be
the
careful.
100. Okay.
Be very conscious.
So phi of
Up, put some space.
200. Up, down. Okay.
Don't crowd all the numbers and the words. You have space, so make them nice.
200
You
is
can
equal
even use
to
other colors so that to make to explain everything in a well-fashioned manner. So on the right side and on the other side can
yes, okay, so we will just use again the same
the
formula we
same
used
formula we
last
use
time.
in 5 and
So
6.
again,
Yes.
so I'll just put it here.
No more, no.
200
Yes, just go
times
directly so we can explain this
first
better.
1 minus 1 over 2, 1 minus 1 over 5, 2, 2, 100, 1 minus 1 half, 1 minus 1 fifth. There. So 200 simplifying times 1 half. So cancel 100. And then times 1 minus 1 fifth, that is
1 minus
4
1 fifth is,
fifths,
yes, 4 fifths.
equals 2 times 100 times 1 half times 4 fifths. So we can cancel these two and then cancel that 0. And use the bracket.
This
Okay,
one
so eventually 100 over 5
is
times 4,
105 is what?
20. So 100 over 5 times
20,
4, 20 times
so
4
20 times 4.
is equal to 2 times 10 times 4. So 2 times 10 times 4.
That's basically the same.
So it's the same.
80, so 80.
Yes, of course.
So
So
there are 80 totatives
they're additives.
to 100.
Yes.
From 1 to 200, yes. So what does this mean?
So what? So I will just explain one.
No, oh yeah, not yet. Explain it in words first, so
Yes.
that we can, before we go, turn to the next, to a fresh page.
100 and 200 are not relatively prime.
Write
So
everything.
yes, wait.
You want me to write
Text.
them? Let me
Yeah, with
explain this one.
text.
So the meaning is we have 80 totatives. So, oops.
Oh, syntax. The line. Red.
Meaning 100 and 200 are
No,
not.
not.
Sorry. Are not. Can you give me some space? Excuse me. Can you sit straight? Not relatively prime. Meaning they have common factors or divisors. No. Since the prime factors of both 100 and 200 are exactly the same, which are the prime factors
2 and 5.
2 and 5, when looking for the totatives, wait, I'll change the color, sorry, let me just edit. When looking for the totatives of 200, or the totient function of 200, meaning the positive integers less than or equal to 200 that are co-prime with 200, you simply have to do exactly the same as how you found the totatives of 100. How? By crossing out
By
what?
crossing out the twos and fives. I will just
The
demonstrate that a
multiples.
little bit later.
By, ay sorry,
Of
what happened?
the line size.
By crossing out all the
Multiples of two and five.
multiples of 2 and 5. We just need to extend beyond 100 up to 200.
So
Meaning,
essentially,
meaning,
all multiples, all of the
cross out,
multiples of both two and five, they just all share the same like quotative table, sort of.
yes.
They're just at different lengths.
So here, as Joshua pointed out,
We're going to demonstrate such a.
oh yeah,
Okay.
here I will just, okay, can I write here?
Yes.
Thus, when we cross it out like that, the totatives of 100 is 40, then the totient function of 200 is 2 times 100, correct?
Yes.
And so this will be 2 times 40, which will be 80. So Joshua, can you demonstrate to us here? If we will really get 40 for the first 100 and another 40 from 101 to 200. So let's cross out all the multiples of 2. Yes, just a single line.
It will be very visible from the.
Let's write all the multiples of 2 that Joshua is crossing out.
I'll just make a.
Yes.
Yes, I found the pattern. I will use
Yeah.
that pattern. Okay, so I'm just
And
crossing out the
then we will
multiples of
count
2.
if there are really 40 left after crossing out all the multiples of the prime factors or divisors of 100. Just see, buddy. Yes, so how about
Multiples of
multiples
5.
of 5? Use a blue,
Slide
light blue, yes. 5, 10,
10, of course, already cancelled.
15,
15,
20,
20. Pattern. How do I.
25,
Ah, okay. So they repeat when
Just cross them outside.
they don't repeat. They don't repeat regularly.
They repeat regularly, but then how it's written here on this table. Sorry for the.
Ah, yes, they form a pattern too. They go like this. They go diagonally. Aha!
Okay.
Okay. Okay, so
100.
yes, 100. I almost forgot 100
It's been
itself.
crossed out anyway. So let's count. There
Uh,
are. Use a yellow.
yellow. Uh-huh. One,
One, two,
two, three,
three, four,
four, five,
five, six,
six,
seven,
seven, eight,
eight, nine,
nine, 10,
10, 11,
11,
12,
12, 13,
13,
14,
14,
15.
15,
Wait lang. I'll just go down small. 16,
16,
17,
17,
18,
18,
19,
19, 20,
20,
21,
21, 22,
22,
23,
23, 24,
4, 25,
25, 26,
26, 27,
27, 28,
28, 29,
29, 30,
30,
31,
1, 2,
32, 33,
3, 4,
4, 35,
5,
36,
6,
7,
7,
38,
8,
39,
9,
40.
40.
There are
40, exactly.
40 indeed totatives.
Okay, so
100
now
meaning
the
those 40 are
yes.
relatively prime to 100. So
So
now
now the
let's do from 100 to 101 to 200.
yes. So now the twos now go directly diagonally. Yes. And then also do the fives. I already
Yeah,
spotted them.
let's do the twos first. The multiples of 2 from 101 to 200.
Dun, dun, dun,
Here we're trying to demonstrate to you, our viewers, how the meaning of the solutions for the Euler's quotient or phi function.
So
Okay,
again,
so let's
let's
count
count again.
again how many
This
are
time
co-prime to
go
100,
yes.
which are also co-prime to 200.
The outside the 100 boundary now. Okay, so 1, 2, 3,
3, 4,
4,
5,
5,
6,
6,
7,
7,
8,
8. Actually, I'll just go diagonally because those are the ones left out.
9,
9, 10,
10, 11,
11, 12,
12, 13,
13, 14,
14,
15,
15, 16,
16, 17,
17,
18,
18, 19,
19, 20.
20,
Okay.
21,
1, 2,
22,
23, 4,
24, 25,
5,
26,
6,
27,
7,
28,
8,
29,
9,
30,
30.
31,
1, 2,
32, 33,
3,
34,
4, 5,
5, 36,
6,
37,
7,
38,
8,
39.
and 40.
Indeed, there are 40 co-prime numbers to 100, which are also co-prime to 200.
100. This one is 101 to 200. So now, In total, that's it. 80.
80, yes.
1 to 200 in total.
That's really true. So, can you show us alternative solutions to this problem, San?
Yes. So, this alternative solution is again based on the dark blue again. So based around the prime factorization. So 100 is 2 squared times 5 squared. So the phi of 100 we can manually calculate. That is just since it's only composed of powers of 2 and powers of prime and another powerful prime and they're both multiplicative. Actually, there's a hidden step here. It's not readily shown. It's actually phi 2 squared times phi 5 squared. So then that is equal to our special formula for
Primes.
perfect powers of primes. So 2 squared minus 2 the first,
And
5
then 5
squared
squared
minus
minus
5 to
5
the
to the
first.
first power.
Yes, so
That will
then that
just
is
be
equal to 4
4
minus
minus
2,
2
25
times
minus 5
25 minus 5.
equals 2 times 20. So that's equals
40.
40.
Yes, there are 40. We saw in the previous page. Can you turn the page, Josh? That there are 40 co-prime numbers to 100 in from 1 to 100.
Okay.
Okay. So
So,
40 totatives of
100.
of 100, meaning there are 40 co-prime numbers or those numbers which will share any common factors with 100 from 1 to 100. Correct, son?
Yes. So now, as there's a special, there are 14. So there's a special property involving GCDs. So that such property is
Can you use a different
the
color? Sure.
is high since GCD AB.
Can
So
you give us an example?
there's this property. Yes, I will give an example. So EG. Let's say
Exempligratia means
yeah,
literally, for example, in Latin.
32, 24. A, B. Okay. So then
This is equal to the
GCD
GCD.
A minus B, so that is 32 minus 24 B, so that's just 24. So let's see. So 32 and 24, the greatest the GCD, I'll just put it again. It's the other ones. Simplify. GCD of 8 and 24. This right side is easy, that's just 8. And then
Yes.
the left side, that's also 8. It's
Yes.
happened. So,
So
yes.
this formula is true. We will use this. Joshua will use this formula for this solving for this and proving this one. So we were saying all numbers which are co-prime. This proves the fact that this will prove the fact that the numbers co-prime to 100 are also co-prime to 200.
Yes, this will explicitly show that all such
Yes.
cases. So, the GCD. Oh, oops, it's too
It's
thick.
perfect. Say just like dark green.
Okay, GCD of 101 and 100 itself is equal to GCD 101 minus 100. So GCD just 1 and
And
100. So
which is
that's equal
really
to 1. So they're
1.
relatively prime, of course.
Yes. So,
And then GCD to
oh,
100.
100.
Oh, 102, sorry.
Oh, sorry.
102, 100 is equal to GCD to
2
100.
100, which is
So that is equal to 2. Then GCD 103, 100 is equal to GCD 3, 100. So that's just equal to 1. They're relatively prime
4.
and then blah blah
Can you do
blah.
it up to no up
Ah, sure.
to 106? Just to prove that this formula really works. So GCD of 104.
GCD foot. Okay. 104, 100 is equal to GCD, GCD, 1, 2, 3. Okay, GCD for 100,
which is
equal to 2.
oh no,
Oh wait, is it 4?
4.
Yes, 4 pala. Okay,
Breakers are the
yes.
least.
Sorry. So 105, 100, 5,
Oh, make your
100,
5 better.
5, equal to 5.
Yes.
And then 106, 100, 100, that is
Close
2.
parentheses.
200.
Yes,
Yes.
all the way
2.
go down. What if you just proving this one? It will go up to GCD of 200 and 100. Applying this formula has the same GCD as 100 and 100.
So this literally shows the proof that we were claiming earlier. 100, the ones that are co-prime to 100, they are in fact co-prime to the other the extended family sort of
So
up to 200.
meaning the numbers co-prime to 100 are also co-prime to 200.
Yes, I not from 200, they are also co-prime to 100.
Yes, all the numbers
Yes.
co-prime to 200 are co-prime to 100.
Yes, so this is 100.
Yes.
So they have exactly the same prime factors, and then 100 happens to be inside the prime factors of 200, so 100. So there are, since oh, there are theta 100
Phi.
ay, theta,
Phi 100
theta, phi
or to
100,
oil social function of 100 is equal to
40,
40 as we've seen above.
40 co-prime numbers to 100. This is the set from 1 to until 100.
And
It's
there are also
range 1 to 100. So these are,
those
oh yes,
parentheses. Can you transfer that one? Taas. Above. Yeah, transfer this one. Oh, it's black. Dito.
yeah, okay. So there
Are also
are also
how many 40
42
co-prime numbers?
co-prime. We can see that they are exactly the same numbers because they keep
To
corresponding.
100
Yes, to 100
in
in the set from 101 until 200. This is 101 to 200.
so in short, how many in all in total?
Of course, 40
40
plus
plus
40
40. Oh,
equals 80.
the plus sign, yes.
Once again.
80 totatives.
So
So
then
yes,
this
there.
the side note here. The fee is multiplicative, so eventually fee of 200 will just be fee of 2 times let's just move this, fee of 100. So it will just become 2 times fee of 100.
Ah, yes.
So
It will
this
be
has
2 times 40.
yes.
Yes, it will be 80. Yes. And another, last but not least, can you turn to the next page?
Our final alternative proof.
Yes, alternative solution is what formula will you use?
We will use another formula for the Euler-Thomson function. So
We have
P1,
discussed
P1, yes.
these things in our lecture on the Euler's quotient or phi function. Check out our video on the lecture about the Euler's quotient or phi function. So it's a matter of just substitution.
So let's go. The phi of 200 is equal to the first prime, which is 2. 2 raised to its
No, put it there so for our viewers. It will become phi of you put the prime factorization so they can learn it really step by step.
yes. So P1 2, K1 3. So the next one will be 2 raised to the 3 minus 1, 2.
2, yes.
And then 5 raised to the K2, which is 2, minus P sub 2, which is again 5 raised to 2 minus 1,
is 1
1. So that is just 8 minus 4,
times
25 minus 5
5, yes.
equals 4 times 20 and equals to 80.
So each of the
This
those
really proves
formula,
it
yes,
must be
yes.
80.
And so we hope you learned a lot. We hope that you appreciate our explanation, detailed explanation of the
The
Euler's
Euler's
quotient
function
function.
and its applications.
Yes. Say bye. Say bye.
Bye.